Hey everyone, welcome back to The Explainer. I am so incredibly excited to jump into today's topic because we're looking at something that is happening inside your head right this very second. Seriously, as you're listening to my voice, we're going to explore the brain's ultimate fast-forward button. We're talking about the biological machinery that dictates exactly how quickly you think, how fast you react, and even how you form the memories that literally make you you. Today, we are demystifying AMPA receptors. But okay, before we zoom way down to the microscopic level, let's start with a big macro level question. Picture this. You accidentally knock a glass off the edge of a table, right? We've all been there. And in a fraction of a second, before you even consciously realize you made a mistake, your hand just shoots out and catches it. Bam! How on earth does your brain process that visual information, make a split-second decision, and command your arm muscles to move, all in less than a second? Well, that everyday lightning-fast reaction is a biological mystery that we're going to solve today.
All right, so here is our roadmap for today. First up, we'll cover the brain's fast-forward button. Second, the push-button door. Third, forging the forest path. Fourth, what happens when AMPA receptors malfunction. And finally, AMPA versus NMDA. Let's dive in.
Section 1. The brain's fast-forward button. Let's introduce the synapse and glutamate. So your brain is essentially this massive, incredibly complex network of about 86 billion nerve cells, which we call neurons. But here's the catch. They don't actually touch each other. They communicate across these impossibly tiny gaps called synapses. The word itself actually comes from the Greek synaptein, which means to clasp together. Pretty cool, right? Now, to send a message across that gap, one neuron releases a chemical messenger. And in your brain, the absolute most common excitatory messenger, the one that yells at the next cell to get excited and fire, is called glutamate. Think of glutamate as your brain's main on switch. But obviously an on switch needs a receiver. And this is where things get fun. Check out the sheer absurdity of this chemical name. AMPA stands for alpha-amino 3-hydroxy 5-methyl-4-isoxodol propionic acid. I mean, come on, what an absolute mouthful. Scientists basically named it after a chemical that artificially activates this specific receptor. But look, you definitely don't need to memorize that whole thing. All you really need to know is that AMPA is the highly specialized, absolute fastest receiving gate for glutamate. It is literally the lock that glutamate fits into on the receiving neuron. Okay, moving right along to section 2, the push-button door. This is the cellular mechanism of speed. I want you to imagine an AMPA receptor as a tiny, donut-shaped protein that's just stuck right through the outer wall of the neuron. Normally, the hole in the center of that donut is sealed tight. But then, step 1 happens. Glutamate arrives. Think of glutamate as a finger pushing a doorbell button on the outside of the store. Step 2, the absolute millisecond that button is pushed, the donut instantly changes shape and the hole pops open. And step 3, positively charged sodium ions, which are just hanging out outside in massive numbers waiting for this, completely flood into the neuron. This sudden rush of positive charge creates this biological process called depolarization. Basically, the inside of the neuron gets less negative, hits a critical threshold, and bam, it fires an electrical signal straight onto the next cell. It's a rapid, instant yes signal. And this brilliantly illustrates exactly why AMPA receptors are the ultimate workhorses of the brain. They give us this vital trifecta. First up, speed. We're talking about doors that open and close in less than a single millisecond. That's 1,000th of a second. That is exactly how you catch that falling glass before it shatters. Second, learning. They power long-term potentiation, which is the actual physical basis of how we form memories. And third, excitatory balance. They keep you alert, sharp, and prevent cognitive sluggishness. Every single time you instantly recognize a friend's face in a crowd or rattle off an answer to a trivia question, this microscopic cellular machinery is firing flawlessly. Just to give you a real sense of the scale here, 80%. A staggering 80% of all the fast, excitatory signals flying around inside your brain right now are traveling through these specific AMPA doors. They are, without a doubt, the undeniable heavy lifters of your consciousness. Let's move into section 3, forging the forest path. AMP receptors in learning and memory. Use it, strengthen it. You've probably heard variations of this, right? It's pretty much the golden rule of neurobiology. So let's look at how this actually builds the foundation of our minds. Say you're learning a new piano scale or studying a really tough math concept. The very first time you try it, the connection between the neurons involved is pretty weak. But each time you practice, those neurons fire together. And that repetitive firing fundamentally, physically alters the structure of your brain through a process called long-term potentiation, or LTP.
Here is the incredible physical reality of what learning actually looks like. When you repeatedly trigger a synapse, your brain literally adds more AMPA receptors to the receiving cell's membrane, and it actually tweaks the existing ones so they stay open longer. It's exactly like a forest path. The very first time you walk through some dense woods, you're pushing branches out of the way, getting snagged, it's slow going. But the more you walk that exact same path, the wider and clearer it gets. By adding more of these AMPA doors, the next time glutamate arrives, a massive wave of sodium floods in instantly. The signal becomes incredibly strong and fast. You don't even have to think about that piano scale anymore. Your fingers just fly. And that right there, that is memory.
Section 4. When AMPA receptors malfunction. The dangers of imbalance.
So the crucial takeaway here is that brain health requires this perfect, delicate tightrope walk of AMPA activity. If there's overactivity, like what happens during a stroke or a severe epileptic seizure, way too much glutamate is released. The AMPA receptors just get stuck open and this massive, completely toxic flood of sodium and calcium rushes in. This literally destroys the neuron from the inside out in a devastating process known as excitotoxicity. But on the flip side, underactivity is equally damaging. If receptor function drops too low, the brain experiences this profound cognitive sluggishness and serious memory issues, which researchers have actually linked to certain forms of depression and schizophrenia.
Because of this razor-thin margin for error, scientists are practically racing to develop medical interventions. But man, it is tricky. For instance, blocking drugs can temporarily shut the AMPA doors to protect the brain from excitotoxicity right after a stroke. But the massive problem? If you block AMPA receptors, you completely block that person's ability to learn or form any new memories. It's a huge trade-off. On the other side of the spectrum, scientists are testing these drugs called ampakines. They're designed to just gently boost AMPA activity to help improve attention and memory for folks suffering from depression or cognitive decline. And we also know from studying rare genetic mutations that if a child is born with improperly built AMPA receptors, it leads to very severe developmental delays. The balance really has to be exact. All right, rounding the corner to Section 5, AMPA versus NMDA receptors, the glutamate dream team. So there is this totally fascinating division of labor going on in your synapses. Glutamate actually binds to both of these specific receptors, but they act completely differently. Think of the AMPA receptor as the worker. It's incredibly fast, it primarily lets in sodium, it opens purely just when glutamate pushes the button, and it provides that rapid yes signal we talked about. But then you have the NMDA receptor. Think of this one as the supervisor. It operates much slower. It lets in sodium, but also calcium. And crucially, it's voltage dependent. What that means is glutamate alone isn't enough to pry it open. The cell has to already be partially excited by our AMPA worker. When the NMDA supervisor finally does open, it triggers this whole chemical cascade that physically builds and adds more AMPA receptors to the membrane. So AMPA does the fast, everyday work, NMDA watches, and when the work is strong and repeated, NMDA steps in and flips the learning switch to make that memory permanent. Okay, let's wrap this all up and summarize what we've uncovered in this explainer. Your very ability to process the words I'm saying to you right now relies on AMPA receptors opening in under a single millisecond, letting sodium flood into your neurons. When you practice, when you learn something new, you are physically building wider forest paths in your brain by moving more AMPA receptors right into those frequently used synapses, and ultimately protecting your brain, maintaining the delicate, perfect balance of all this activity, avoiding the toxic flood of overactivity and the sluggishness of underactivity.
You know, when you think about it, you are quite literally the architect of your own mind. Every single habit you form, every skill you relentlessly practice, and every single member you cherish is written in the physical language of AMPA receptors being added to your microscopic synapses. So I want to leave you with this final thought. Which of your brain's forest paths will you choose to strengthen today? Thanks for focusing in with me, guys, and as always, keep learning.